These are the notes for AP Calculus on the topic of piecewise functions. So the example says, write a piecewise function for the given graph, and then state the domain and range of the graph. Okay, so these are called piecewise functions, like the name suggests, because they have more than one piece to them. So what I'm going to do on your notes as you write it down as well, is for each piece I'm going to use a different color to represent it, and we're going to just work on one piece at a time. So we can see the first piece is this linear segment right here, in red, and then we've got a second piece right here, and our third and final piece. We don't need to make this two separate pieces, it's all just one straight line now, one linear equation. So the first thing to write down is what part of the domain does each piece apply on. And the domain, remember, refers to the x values. So if you look at this first piece in red here, you can see the lowest x value it starts at is 0. So you'd say 0. If you go from left to right, it's like going from low to high, you're just going to use less than. You won't have to use greater than on these. So 0 is less than, and it actually does equal 0 right at that point. Otherwise, if it didn't, there would be an open circle to show it doesn't quite reach there. So since it does reach that, it's included, so we put less than or equal to. Domain is x, and x is less than. Notice where the first piece in red here stops is at an x value of 4, and it does equal that. Now let's write the equation for it. So it's a linear equation, so you can either use point-slope form or slope-intercept form, but I think slope-intercept form tends to be a little bit easier. You use just y equals mx plus b, where m represents the slope and b represents the y-intercept. Well, sometimes you can just look at the graph to figure out the slope. If you look at the graph here, you can see the slope of this linear segment. It goes down 1, 2, 3, and right 1, 2, 3, 4. So the slope would be negative 3/4. And then x, and then b is the y-intercept. Well, for this piece, we can tell exactly where the y-intercept is. It's right there at 5. So plus 5. So there's the equation for the first piece of this piecewise function. Now let's move on to the second piece. And notice this 0.42 is actually on both pieces. So when we start at 4, that's the x value the green piece, the second piece starts on. Because it's shared by both pieces, this or equal to could go on either this less than or on this less than. It doesn't matter which. Just choose one or the other because both points have it in common. So 4 is less than x, and the x value this one stops at is 9. So x is less than, same thing with 9. Since it's shared by both of these pieces, this 0.92, we can include it either on this piece or on the next piece. So I'm just going to include it on this piece so we don't forget about it later. And this is just a horizontal line. So this one's a lot easier to write the equation of. Notice the y-coordinate is always 2 on that line, hence the equation of a horizontal line, y equals 2. And finally, the last piece, the lowest value is 9, so we'd start at 9. We already included it here. So it's less than x, which is less than, and notice the arrow shows it keeps on going forever, so that's all the way to infinity. And we don't put the equal to on the infinity because the number can't equal infinity, because that means it just means going on forever. Just like we never put, when we're writing interval notation, we never use a bracket on infinity because you can't equal it. We always use parentheses. All right, now this piece, again, if we start out with the slope-intercept form, y equals mx plus b, it might be a little harder to tell what the slope of this is. So remember, you can always use the slope formula for a linear equation, where the slope m is the difference of the y-coordinates, so y sub 1 minus y sub 2, divided by the difference of the x-coordinates, x sub 1 minus x sub 2. So you can start with either one. I'm going to use this as our first point. So the difference of the y-coordinates would be 4 minus 2. And just going in the same order for the x-coordinates, the difference of the x-coordinates would be 13 minus 9. 4 minus 2 gives you 2. 13 minus 9 is 4. 2/4 reduces to 1/2. So the slope here is 1/2 x, and now we just need to know what the y-intercept is. Now, unlike the first piece where we just looked at the graph and could see the y-intercept was 5, this one, it's harder to tell because you'd have to like extend this line all the way like this to see where it would actually intersect the y-axis. And sometimes it's hard to tell exactly where that is. So for now, I'm going to just leave that as plus b. But the way to figure it out exactly algebraically is to just substitute in one of these points that are on the line that we know. Either one works. So I'm going to use 9, 2 to substitute in for x and y. So the y-coordinate is 2 when the x-coordinate is 9. And then on the right side, 1/2 times 9 simplifies to just be 9/2 plus b. And to make this easier to solve for b, I'm just going to get a common denominator. 2 is the same as 4/2. 4 divided by 2 is 2. And then when you subtract 9/2 to isolate the b, 4/2 minus 9/2 gives you negative 5/2 for b. And then we can substitute that right in here. So our equation for this piece is y equals 1/2 x minus 5/2. Now we've got all the equations of all the pieces, so let's just put it together to write our piecewise function. Notice right here it says, we're writing it as f of x. If it didn't specify, you could use f of x or g of x or whatever you want to use. And notice this is x right down here, it's a little hard to see. So f of x, notice we've got 3 pieces, so write an open brace here and leave yourself enough room for 3 different lines. And the typical way of writing piecewise functions, just the same order we went here from left to right on the graph, typically on the function goes from top to bottom. So let me show you a common mistake sometimes I'll see students make. And they'll write, for the first piece, they'll write this. A equals negative 3/4 x plus 5. The problem with that is it's redundant. Okay? We already have f of x equals, which is like y equals already. So there's no need to put another y equals. It's already there for all 3 pieces. So instead, all you have to do here is just put in the negative 3/4 x plus 5. And it's already got y equals right there. And then after you put the equation, you use one of 2 words. You can either say for or if. Either one is fine. So for the interval, we write down now. 0 is less than or equal to x, which is less than or equal to 4. So we know this function applies on the interval from 0 to 4. Then the second piece was y equals 2, but again, we don't need the y equals. It's already here. So just put in 2, and then for the interval on this one is 4 is less than x, less than or equal to 9. And then the last piece, 1/2 x minus 5/2. For, now on this one, you could write it the way we wrote here, 9 is less than x less than infinity, that's fine. But typically on inequalities, if there's any infinities or negative infinities, they'll usually leave them out. You usually won't see them written in interval notation, you'll see it, but not in inequality notation. Oftentimes they'll just take this part, which means the same thing. So this is saying 9 is less than x, but another thing they'll also often do is when it's not a compound inequality between 2 numbers like these two, they'll usually put the variable on the left. So rather than say 9 is less than x, that's the same as saying x is greater than 9. But you could say 9 is less than x, that's correct also. Because if x is greater than 9, it already kind of implies that it's all going all the way to infinity. So there's our piecewise function, that's the first thing. Now we just have to write down the domain and range. So for the domain, remember all the possible x values. Going from left to right, we can see the furthest left it goes is right here with an x value of 0. And that's included, so we use a bracket. As we head right, I see it keeps going right forever, but you do that arrow, so 0 all the way to infinity. Oops. Sorry, I accidentally used a bracket. For infinity and negative infinity, you always use parentheses, because you can't include it. You never can quite reach there. Then the range. Here you go from low to high, the lowest y, looking at the y values, all the possible y values. The lowest y value it reaches right here is 2 with a bracket since it's included at a bunch of different points. Here it equals 2. And then you can follow this one. It looks like it stops at 5, but if you look over here, the graph actually keeps going up to infinity. All right, let's take a look at one more of these where we write in a piecewise function. Okay, on this one, let's see how many pieces we need here. Notice it's scaled by 10, a little different, and notice another difference, we've got v of t and t rather than x and f of x. So the first piece is this line segment right here. The second piece right here. The third piece right here. And this one needs a fourth piece right here. I'm going to use the same color since they're both horizontal lines for both of these two pieces. All right, let's look at the first piece here. X value starts out as 0, except it's not an x value, it's a t value. Okay? So notice it'd be 0 is less than or equal to t, which is less than or equal to, it stops at a t value of 30. And again, using, normally it's y equals mx plus b, but here it would be mt plus b. And we can see the slope on this one. This one you can probably tell just by looking at the graph. You can see the slope, it goes up 70 over 30. So 70 over 30 reduces to 7/3. So it'd be y equals 7/3 t. And the y-intercept, well, if you just look right here, it intersects the y-axis at 0. So you don't need anything, just 7/3 t. Then the second piece starts at a t value of 30. We already included it here, so we don't have to include it here. And it stops at a t value of 50. I'll include it here, so I don't have to include it later. Then this one's just a horizontal line, so it's y equals, in this case, it equals 70. Then the next piece starts at 50. We already included on this piece, so we don't need to include it here. And it stops at 100. Here you might want to use the slope formula. So if again we start off with y equals mx plus b. So if we use the slope formula here, the difference of the y's, so 70 minus 20 over, divided by the difference of the x's, 50 minus 100. That gives us 50 over negative 50, reduces to negative 1. So we can substitute that in here for the slope. We just calculate as negative 1. So just negative x. And then the y-intercept. This one you might be able to tell if you use a ruler or something to see exactly where it intersects the y-axis if it kept going, since it's just a simple slope of negative 1. But to get it exactly, algebraically, you would just substitute in one of these points, either 50, 70, or 120 for x and y. Whoops, actually this isn't an x, is it? Sorry about it. Technically this is a t here, not an x. Sorry about that. I wrote it up here, but I forgot down here. So if you do accidentally put x here, it's not the end of the world as long as you remember when you write your final answer for the function to be all in terms of t rather than x. And then we can substitute in one of these points, either 50, 70, or 120. So I'm going to use 50, 70. So y is 70 when t is 50. Add the 50 over, gives you b equals 70 plus 50 is 120. And just substitute that right back in here. So you get y equals negative t plus 120. And finally, the fourth and final piece here starts at 100, less than t, and this one stops at 130. Notice there's no arrow there. And it does actually equal it because it's not an open circle. And this one's just a horizontal line. So it would be y equals, the y coordinate equals, you can see is 20. Now, let's write our piecewise function. Let's put all four pieces together. This one, notice, is v of t, which we'll also often see in calculus stands for velocity, where t represents time. This time, when you write open brace, leave yourself enough room to write four pieces. So the first piece we got was 7/3 t. And that applies for the interval 0 less than or equal to t less than or equal to 30. The second piece we found was just 70 for the interval 30 less than t less than or equal to 50. The third piece we found was negative t plus 120 for 50 less than t less than or equal to 100. And the fourth and final piece was just 20. For 100 less than t less than or equal to 130. So there's our piecewise function. And now, again, it just asks us to write the domain and range. So the domain, the lowest x value, or in this case t value it starts at, is 0, included, so we use a bracket. And it keeps on going, but it doesn't go to infinity, it stops at a t value of 130. It's included. And then the range, going from bottom to top, low to high, the lowest y value reaches is 0, and the highest it reaches is 70. So it starts out with 0 with a bracket included, and it does also reach 70 at several points. So there's your range. Now let's take a look at going the other direction. Those we had the graph when we wrote the equation. Now let's look at the equation and try to come up with a graph. And again, we'll determine the domain and range. So it says identify the breakpoints of each piecewise function. Now this is not a technical term here, it's just a term I made up because as far as I know there's not a specific name for these places where the function breaks into pieces. So I call them breakpoints because they're the points where the piecewise function breaks into more than one piece. And then we're also going to determine its domain and range. But notice at the top it says to graph piecewise functions, evaluate each part of the function at its breakpoint or breakpoints, and then find additional points as needed. So I wanted to come up with a name for them because they are so important when you're graphing these piecewise functions. You need to know where the function's at these breakpoints, because that's either going to be where a function, each piece starts or stops. So the way we can graph this, first write down the interval it applies on. Just go from top to bottom, which is like going from left to right. And as you're doing these, make sure you completely graph one piece before you move on to the next piece. Otherwise, you might accidentally connect two different pieces that don't actually connect. So 0 is less than x less than 6. So this piece has two breakpoints associated with 0 and 6. So if we substitute in 0 first, 1/2 times 0 gives you 0. So we substitute in 0, and we got 0. So at the point 0, 0, we'll start to graph it. But at the breakpoints, you have to determine if they're going to be regular points, just closed circles, or they're going to be open circles, not included. The way you tell is just by looking at the or equal to. If it has or equal to, that means it could equal 0 and would be a normal closed point. But if it doesn't, like in this case, then it's going to be an open circle. Now we exaggerate the size of the circle. It's not really that big, so we can see it, because if we didn't do that, it'd be so small you wouldn't be able to tell it's there. Okay, now let's substitute in the other breakpoint of 6, because this piece has two breakpoints associated with it. 1/2 times 6 gives you 3. So we substitute in 6, and we got 3. And again, at 6, 3, since that's a breakpoint, let's determine whether it should be an open or a closed circle. So at 6, 3, again, notice it doesn't have the or equal to there, so it's not included. So again, it would be another open circle at 6, 3 right here. And then we have to look at the equation, see if we need additional points or not. Well, 1/2 x is like y equals 1/2 x. That's just a linear equation. And all we need is 2 points on a linear equation, so we can sketch the graph. But these breakpoints show you where to start and or stop the function. In this case, this is where it starts at 0, this is where it stops, so we draw the linear equation, but we only graph it in that interval. Don't go beyond that. All right, so we're done with that piece. Now we can move on to the next piece. The next piece, the interval it applies on, is x is greater than or equal to 6. Okay. So you first substitute, and this one only has one breakpoint of 6, but when you try to substitute 6 into this piece, there's no x to substitute in for. It's always 3, so you get 6, 3. And it's a breakpoint, so to determine if it's open or closed, notice it has the or equal to. So that's a regular closed point. And this one, you can see additional points. If you plug in 7, it has to be greater than or equal to 6. So 7 would give you 3, 8 would give you 3, and 9 would give you 3. Remember, if it's y equals 3, that's just a horizontal line. However, we don't draw the entire horizontal line, y equals 3, only where x is greater than 6. So starting at our breakpoint and just heading to the right. And since it keeps on going forever that way, we put an arrow on it to show it keeps on going. All right, now let's take a look at the domain and range, now that we've graphed it. So for the domain, looking at the x values, the lowest x value start out is 0, but notice it's not included because it's an open circle. So it would be a parentheses, 0, and it keeps on going right forever. So 0 to infinity. And then the range, all the possible y values, go from bottom to top. Lowest it starts at is 0. Again, it's not included though, so parentheses. Goes up. In this case, it doesn't go up to infinity. It levels off at 3, and 3 is as high as it gets. So it stops at 3, and it's included, so a bracket. So I forgot to mention here, this is not always going to happen. Okay? On this particular one, at the breakpoint, they actually meet up. But on other functions, we'll see, they don't meet up. It just depends on the function. So this time, the closed point actually filled in an open circle. All right, let's take a look at a few more of these. This one just happens to be in terms of t, so in this case, this would represent the t-axis rather than the x-axis. So in this case, there's only one breakpoint, just 0. So let's start with t is less than or equal to 0. First substitute in the breakpoint of 0, so 2 times 0 plus 3 gives you 3. So 0, 3. And notice it has the equal to, so this is a regular point, so it would be closed at 0, 3. And if we look at this equation, 2t plus 3, we can see that's just a linear equation, but we need at least one more point. But one reason why I have you write this at the top is to remind you what kind of numbers you can substitute in. We plugged in the breakpoint, so other numbers we substitute in for t have to be less than or equal to 0. So what else could we use? We could use, well, -1. If you use a number that doesn't fit this, it's going to give you the incorrect graph. So -1. Okay. So that's 2 times -1. -2 plus 3 gives you 1. So -1 gives us +1. And notice I didn't ask whether that should be open or closed because it wasn't a breakpoint. If you're substituting additional points that are not breakpoints, those are just regular points. Those are never open. So now we have enough to graph it. Remember, it's got to stop at this breakpoint. It only applies where t is less than or equal to 0. Like that. And then put an arrow here showing it keeps on going further. Now we're done with that piece. Let's move on to the next piece. This one is t is greater than 0. So we first have to substitute in the breakpoint of 0, which gives you the square root of 3. Now, to help us graph this, let's approximate that. Square root of 3, well, square root of 1 is 1. Square root of 4 is 2, so it's between 1 and 2. But 3 is a little closer to 4 than it is to 1, so it would be closer to 2 than it is to 1. So it's around 1.7. That's just to help us graph it. So it's at 0 and then around 1.7. And it's a breakpoint, so would it be open or closed? Notice it doesn't have the equal to, so it would be open. So 0, 1.7, so it doesn't have to be exact about right. Right there. Now, let's take a look at the equation. Well, square root t plus 3. Notice square root graph, that's like our half parabola. So usually on a curve, you'll need at least 3 points. So we have to substitute in some more points, but let's try to get some that work out to be perfect squares so we don't have to approximate them. But notice we can only plug in numbers greater than 0. So let's try to make it a perfect square. Well, how about if we substitute in 1? Because then that'll give you the square root of 4, which is exactly 2. So we substitute in 1 and 2, so we plot the point 1, 2. Notice it's not a breakpoint, so it's not going to be an open circle, just a regular point. And then when you substitute in, let's see, what else can we plug in the perfect square? Well, the next perfect square after 4 is 9. So if we substitute in 6 for t, that'll give us the square root of 9, which is 3. So we substitute in 6, and we got 3. Again, not a breakpoint, so it's just a regular point. And then we can graph it. You can see we see part of that square root graph. Starting at 0, the breakpoint there, and then curving off up like that. Now let's see why it looks the way it does. Notice that plus 3 in there would normally shift the graph 3 to the left. And the square root graph normally starts at 0, 0, and it still does switch 3 to the left. It's just this part right here we don't see because we're only looking at the part where t is greater than 0. So that's what happens on these piecewise graphs. You're looking at, just like this, you only see part of the line. Here we're only seeing part of the square root graph. What's going to happen, let's say for instance on the line, you drew it too far. Well, you might recall the vertical line test, remember, in testing to see if something is a function. If you can draw a vertical line, to be a function, it can never cross the function more than once, which in this case it doesn't, right? So we're okay. So after you graph each one of these, easy way to make sure you didn't graph any of the pieces too far beyond their domain is to apply the vertical line test. Because for instance, let's say we drew this line beyond the breakpoint here like that. Then notice what would happen. It wouldn't pass the vertical line test. It wouldn't be a function. So we know that can't be correct because this is a function. Okay, now finally let's put down the domain and range of this one. The domain, notice this one goes left forever, so it starts at negative infinity. Keeps on going right. Notice we don't have to stop at 0 because there is a point there. And it goes right forever, so negative infinity to infinity. And the range, this one heads down to negative infinity. Just keep following it up. Now it looks like it stops at 3, but look and see if there's anywhere else you can hop onto. And notice right here, has a y value of 3, so it keeps going up all the way to infinity. Okay, let's take a look at another piecewise function now. The next one's a little bit different type of piecewise function. Because notice rather than inequality signs, we've got x does not equal 2 and x equals 2. So let's see how that affects our graph here. So x does not equal 2. All right, well 2 is the breakpoint, so we substitute in 2. When you substitute in 2, you get 2 minus 1 is 1, cubed is 1. So we get 2, 1. And then to see if it's an open or closed, same thing applies. Does it have the equal to? No, it has a does not equal to. So at the breakpoint 2, 1 is going to be an open circle. But on this one, to get additional points, let's take a look at the equation. X minus 1 cubed, you remember the cubic graph looks kind of like this. So it's going to look something like that. So we need at least 2 more points. So let's see what else we can substitute in. Well, if we substitute in anything but 2, so how about 1? If we substitute in 1, you can see that would be nice to give us 0. So 1, 0. And you could try substituting in 0. I'll give you negative 1 cubed. That would be negative 1. So 0, negative 1. That might not be quite enough to see what the graph looks like, unless you notice the transformation here. Notice it shifts, this -1 right here, shifts the graph 1 to the right. So rather than 0, 0, it shifts over here. So if you know that, rather than finding additional points, you can say, oh, it just shifted over here, and it's still going to look like our normal cubic graph like that. So that's what it looks like. It applies everywhere but 2, right? Which is why there's a hole there at 2. That's the one x value we can't plug into that graph. Now let's look at the other piece for x equals 2. Well, here when you try to plug in 2, there's no x to plug into, you just get -3. So 2, -3. It's got the equal to, so it is a closed point. And then, well, what else could you substitute into this piece? Well, right here. Nothing, right? You can only plug in x equals 2. So whenever you have a piecewise function like this, on the piece that says equal to a specific number, it's just going to be a point. Because there's no other x values we can substitute in. Sometimes that point actually might fill in the hole, but oftentimes it doesn't, like this one. All right. Now, let's write down our domain and range. The domain on this one goes left forever, so -infinity. Keeps going right. You might think, well, do we need to stop at an x value of 2 here? You would, except notice it is defined because of this point here. At an x value of 2, there is a point. So we don't have to stop at 2. If that point wasn't there, then you would need to stop at 2. But in this case, you don't have to stop there, and it goes right forever, so -infinity to infinity. But the range heads down forever to -infinity, starts there. And if you keep going up, notice we hit this hole, but for the y value is 1. And if you look across the whole graph at y equals 1, there's nowhere the function has a y coordinate of 1. So you would have to stop at 1 with a parentheses because it's not included. And remember, when you have more than one interval, you put a little u between them. And then we're going to go from 1 all the way up to infinity. All right, let's take a look at the next one. So far, the piecewise functions we've looked at have only had 2 pieces. Now let's take a look at a couple that have 3 pieces. So let's write down, this first one applies where x is less than -3. So remember, first substitute in the breakpoint of -3 for x. Gives you 9 minus 9, 0. So -3, 0. Notice it doesn't have the equal to, so open circle. Now let's look at the equation. That's the only breakpoint. But notice it's x squared minus 9. Remember, that's going to be like a parabola-like shape. So ideally, we'd want 3 points. This is a curve to graph it. So let's substitute in something. Notice we have to plug in numbers less than -3. So how about -4? That gives you 16 minus 9 is 7. So -4, 7 will be the next point. A little bit off our graph. And it's not a breakpoint, so you don't have to worry about it being an open circle. But notice if you try to plug in -5 to get another point, you can get 25 minus 9. It's going to be 16, which is way off the graph. So another approach, if they're not going to fit on the graph 3 points, if you think about what this minus 9 would do to the graph, it would take the normal parabola, which starts at 0, 0, and it would shift it down 9 units, so down here, right? And then would normally be a graph that looks like this. Parabola, curving up. That, and then it would go like this. Something roughly like that. But we're not going to see the entire parabola like we normally would. We're only going to see the part where x is less than -3. So we're only going to see this part. But that gives us an idea of what this part looks like, the curvature of it. So it's pretty steep. So let's just go back. And now we know we're only going to see this part of that parabola. Okay, so we're done with that piece. Let's move on to the next piece. This one applies where negative 3 is less than x, which is less than 2. So this one has two breakpoints associated with it. Let's substitute in both. Let's substitute in negative 3. That gives you negative 5, so negative 3, negative 5. And notice that negative 3 is a breakpoint, and it doesn't have the equal to, so an open circle at negative 3, negative 5. Now let's substitute in 2 for x. 2 minus 2 gives you 0. So 2, 0. Also doesn't have the equal to, so another open circle. And if you take a look at the equation, notice it's just like y equals x minus 2. That's just a linear equation, so 2 points is sufficient for a linear equation. But again, when you're graphing it, we're not going to graph the entire line, only between the two breakpoints here, which is why it's so important to get where those are. So that's the only part we're going to see. And notice, it intersects right there at negative 2, which it should, right? Because that's the y-intercept, or it shifts it down 2. All right, let's take a look at the last piece now. This one applied where x is greater than, greater than or equal to 2. And we substitute in 2 for x, the breakpoint first. You get 4, so 2, 4. And this one does have the equal to at the breakpoint, so at 2, 4, it will be closed. It'll be a regular point. Now, this one, you can see it's linear also, but we need at least one more point. Make sure you plug in numbers according to this restriction after the breakpoint. Has to be greater than or equal to 2, so let's try 3. That would give you 6, so we substitute in 3 and we got 6. And it's not a breakpoint, so it's just going to be a regular point there, 3, 6. And then, as we know it's linear, so just graph the straight line goes between those. And notice it only applies where x is greater than or equal to 2. So start at the breakpoint and go where x is greater than or equal to 2. With an arrow there. Now let's finally put the domain and range. This one's a little more interesting for domain and range than the other ones have been, with 3 pieces here. So the domain, from left to right, notice it goes left forever, this part of the parabola. But notice when we hit negative 3, there's 2 open circles. So there's nowhere where the function has an x-coordinate of negative 3. We can see it even by looking right here. Notice since neither one of these has or equal to at negative 3, there's nowhere to plug in the negative 3. So we do have to stop at negative 3 with a parentheses not included, and then a u for the next interval. And then from negative 3, keeps on going. Now at 2, notice we don't have to stop because they're not both open. This one's closed. So it actually does have 2 in the domain. And then it keeps on going to the right forever. So from 2, sorry, what? Not from 2. From negative 3 right here all the way to infinity. And then the range, so the range, notice there's no arrow heading down. The lowest this function gets is right here at negative 5. And since it's an open circle, the parentheses. And if we keep heading up, notice we stop right here at 0, and you look, is there anywhere else where the function has a y-coordinate of 0? In this case, there's not, because both of these are open circles, so we do have to stop at 0. Or the parentheses not included, and then a u for union for the next interval, resumes right at 0, and then heads up to infinity. All right, let's take a look at one more. Another one with 3 pieces, so let's start with the first piece. Negative 3 is less than x, which is less than 1. So let's first substitute in the breakpoints. Negative 3. And then 3 divided by negative 3 is negative 1, so we get negative 3 and negative 1. And notice it doesn't have the equal to at negative 3, so that's going to be an open circle. Now let's substitute in the other breakpoint, 1. So 3 divided by 1 gives you 3. So 1, 3. Also doesn't have the equal to, so another open circle at 1, 3. But if you look at the equation, 3 over x, that's similar to the graph of 1 over x. And remember 1 over x, remember the graph of y equals 1 over x. Here's your x and y axis, looks something like this. And notice, right here, this one's just going to be, the value's going to be a little bit bigger because it's multiplied by 3, but it's going to have the same shape to it. Notice right here, on the graph, it's got a vertical asymptote, which is right in the middle of ours. So if you substitute in 0, you can see that for x, that's between negative 3 and 1, but 3 divided by 0, nothing times 0 gives you 3, so that's what we call undefined. And so that creates a vertical asymptote at x equals 0. It's a dotted line you can draw right there. And that's going to help guide our graph. So normally, what this would look like this, if it wasn't part of a piecewise function, through these points, it would normally look like this. However, we're not going to see the entire graph, remember, because we're only looking between negative 3 and 1. So we're only going to see from negative 3 to 1, this piece, and this piece. All right, now let's take a look at the next piece. This one applies on the interval 1 less than or equal to x, which is less than 5. So it's negative. First thing we should plug in is the breakpoint 1. So we substitute in 1. Well, absolute value of negative 1 gives you 1 times this negative 1 is negative 1. So 1 is negative 1. And it has the equal to there. So that would be a closed circle at that breakpoint at 1, negative 1. Then let's plug in the other breakpoint of 5. 5 minus 2 gives you 3. Absolute value of 3 is 3 times negative 1 gives you negative 3. So 5, negative 3. But this one doesn't have the equal to at the breakpoint, so that would be an open circle at 5, negative 3. And then you can plug in some more points. But let's take a look at what the equation looks like. Well, that's an absolute value. Remember, those linear absolute values look like these. So you could plug in other points, 0, sorry, not 0, 2, 3, 4, in between here to get what the graph looks like. That would work. Or, if you recognize what this is going to do, look at the minus 2, takes that v that normally looks like this, right? But it's going to shift it 2 to the right, and then that negative out in front reflects it across the y-axis. So rather than opening up, it's going to open down. So normally it would look like this. But we're not going to see that entire graph, right? We're only going to see between 1 and 5, so just this part of it. That's why it's so important to have those breakpoints plugged in. Tell us where to start and stop. And finally, the last piece, we've got the square root of 9 minus, oops, sorry. We have to put down the interval first. We've got x is greater than 5. So 5 is your only breakpoint on this piece. So if we substitute in 5, we get square root of 4, which is 2. So 5, 2. And, whoops, I accidentally erased some of this. I'm just going to see that part. There we go. So 5, 2. And let's try to plug in other numbers greater than 5 that will give us perfect squares. Well, this gave us the square root of 4. If we substitute an 8 for x, that'll give us the square root of 1. So square root of 1 is 1. So 8, 1. Oh, I forgot to put 5, 2, sorry. 5, 2 would be an open circle because it's not included. Doesn't have the equal to. This is not a breakpoint, so it's just a regular point at 8, 1. And let's try to get one more point since we know this is a curve, like a half parabola-like shape. So we could substitute 9, you get the square root of 0, which is 0. So 9, 0, again, it's not a breakpoint, so just a regular point. So you can see that 9 shifts it this way, 9 to the right. And that negative makes it open the other way. So be careful. A common mistake on this one is students will graph it like this. The problem with that is, notice, past 9, like if you substitute in 10 for x, that gives you the square root of -1. That's imaginary. Okay? And imaginary numbers don't show up on the graph here. So 9 is actually the largest number we can plug in to get a real number. So we're not going to have that part. It's just going to stop right there at 9. All right, now let's write down the domain and range. The domain, as we head from left to right, the lowest x value we have is -3. It's not included because it's an open circle, so with a parentheses. As we head from left to right, notice we also have a vertical asymptote at 0, which means you can't plug in 0 into the function. Remember, it was undefined. So we have to stop at 0 with a parentheses. Then then we resume right at 0. Just keep going. 1 we don't have to stop at because there's a closed circle there, so it does have an x value of 1 right there. Keep going to the right. Oh, notice at 5 they're both open circles, so there's nowhere to substitute in the 5. You can see it again right here. Neither of the 5s have the or equal to, so you have to stop at 5. And then a u, and then from 5, it doesn't go to infinity, it stops at 9, and it's included, so with a bracket. And then the range, well, this one starts at -infinity because of that arrow. And when you're working out the range, sometimes it's going to be a little bit more challenging than the domain because you have to hop on different parts of the function more often there. So as we head up, what you usually want to do is go from bottom to top. Just follow that function along until it stops, if it does. And if it stops, then see if there's another function you can hop on with the same y value, like left and right. So here it looks like it stops at -1. But then if we look left and right, we can see we can hop onto this one, and it does have a y value of -1 right there, close point. So we do not need to stop at -1. Keep going. Looks like it stops at a y value of 0 there. Look left and right, and notice we can hop on right here. It does have a y value of 0, and it keeps going up. Looks like it stops at 2, and now at 2, notice there's nowhere else on the function that has a y value of 2. So we do have to stop at 2, and it's an open circle there, so with a parentheses. And then notice, this one doesn't resume right after 2. The next y value we have, there's this gap between 2 and 3 with no y values, is 3, with a parentheses, so this is not included. And then from 3, it goes up to infinity. And that concludes the notes for AP Calculus on the topic of piecewise functions.